Okay, we're going to go ahead and get started here on 6.2, the homework. Going to be evaluating some trig integrals. First one, number 1, is integral sine squared x times cosine cubed x. So sine squared x times cosine cubed x. See if I can find any good markers here. Dx. All right, so going through the steps, the procedures that the notes give you says that if you have sine or cosine raised to an odd power, right? Or sorry, the first step says if cosine is odd, then we're going to factor out one of the cosines. So we do have cosine as an odd power here. So we'll go ahead and factor out a cosine here. So let me take one cosine. So this integral is equal to sine squared x times cosine, times cosine squared x times cosine x dx. So I've factored out one of the factors of cosine, and I'm going to make a substitution that u will be equal to sine x. The derivative of that is cosine x dx, which I actually have right here. So now it's just a matter of rewriting everything here in terms of sine so that we can replace these things with u's. So this is already going to be u squared. Cosine squared, though, needs to be switched. So what I'm going to use is the Pythagorean identity, rewriting cosine squared x as 1 minus sine squared x, and then rewriting everything else. And now you can see this is going to be u squared, then 1 minus u squared, and then this here will be the derivative of u, so du. So now I'll go ahead and rewrite this integral. So this will be equal to, in terms of u, it'll be equal to u squared times 1 minus u squared times du. And now this is just powers. This is just a polynomial in u. So what I can do is I can distribute the u squared through to remove the parentheses. So u squared minus u to the 4th du. And then I just integrate those term by term, and I use the power rule. So the antiderivative now is 1/3 u cubed minus 1/5 u to the 5th plus some constant. And now just replace u with sine x. So we get 1/3 sine x, but cubed, so we put the 3 here, then minus 1/5 sine x, but to the 5th power, so put 5 here, and then plus my constant of integration. So that's number 1. Now I'm going to do number 2. So for number 2, we have, let's see here, sine to the 3rd, cosine to the 4th. Was it theta? They're using theta. Sine to the 3rd theta times cosine to the 4th theta d theta. So this time the sine is the thing that's being raised to the odd power because it's being cubed. So this time I will factor out a single factor of sine instead. So this can become sine squared theta cosine to the 4th theta. Factored one sine out, so here it is, sine theta d theta. And then I will make the substitution that u will be cosine theta this time. And the derivative of that is negative sine theta d theta, which we almost have. We have a positive, and this is negative, right? So I'm going to just multiply both sides by -1. I need a new marker. I don't have any good markers around here. And so I can replace the sine theta d theta with negative du. I can replace the cosine theta with u, so that'll become u to the fourth. I just need to be able to get rid of that sine squared. So again, I'll use the Pythagorean identity to turn sine squared into 1 minus cosine squared. And then I still have the cosine to the fourth. Then I still have sine theta d theta. And then at this point, we can rewrite the entire integral in terms of u. So this integral becomes, in terms of u, 1 minus u squared times u to the fourth. Then this is negative du, so I'll put a negative on the outside of the integral, negative du. And then what I'll do is I'll multiply u to the fourth through. So this becomes negative integral u to the fourth minus u to the sixth du. And then one more thing I'm going to do before I integrate, because this is a negative, is I'm going to multiply it back through, make that a minus u to the fourth and a plus u to the sixth. And then I'm going to rearrange the order of things. So that integral becomes positive u to the sixth minus u to the fourth du. And then at this point, I integrate using power rule. So this will be equal to 1/7 u to the seventh minus 1/5 u to the fifth plus c. And then this is going to be 1/7. U was cosine theta, so cosine theta to the seventh minus 1/5 cosine theta to the fifth plus c. I think that was an exam problem, if I'm not mistaken, for my face-to-face class. And that's it. We're done. All right, so I'm moving along. Number 3. All right, for number 3, let's see here if I can maybe get a decent marker here. I doubt it. Okay, integral sine to the seventh theta, cosine to the fifth. And they have limits of integration numbers there, but we're ignoring those for now. So what I'm going to do now is realize that I have both the cosine and the sine that are both odd powers. And so really it's up to me to decide which one I want to use. Do I want to use the sine or the cosine as my u? And I have the choice because they're both odd. So I'm going to go ahead and use the sine because I like the derivative of sine. The derivative of sine is just cosine. I won't have to worry about any negatives. So I'm going to let u be equal to sine theta. Du is equal to cosine theta d theta. So in doing this, I need to peel off that cosine, one of the cosines here, out, so that I can have my du sitting there. So cosine theta d theta. And now it's just a matter of turning everything in terms of sine. So sine to the seventh is no problem. Cosine to the fourth, though, I can't use that. So what I'm going to do is I'm going to realize first that cosine to the fourth is really cosine squared, and then cosine theta d theta. Now I can use Pythagorean identity here. So we have integral sine to the seventh theta, and then this is 1 minus sine squared theta, but then that entire quantity squared, and then cosine theta d theta. And now I have everything in terms of u. In terms of sine, which is u. So this will be u to the seventh, this will be u squared. And then this right here is exactly du. So I'm going to rewrite the integral now. I'm going to rewrite it in terms of u. So this becomes u to the seventh, that's this, parentheses, 1 minus u squared, parentheses, squared, and then cosine theta d theta is du. And this is very much like the last problem, but I can't distribute the u to the 7 through because I have a squared here. So I actually have to square that first. And because I can square it, that's what makes this problem doable. If that were to the 100th power, I'd have to do something else. So when you square this, right, you have to multiply it times itself. You get 1 minus 2u squared plus u to the 4th du. And then you can distribute the u to the 7th through. So you get integral u to the 7th, it's here, then minus 2 u to the 9th, I'm adding the exponents, plus u to the 11th du. And then I can integrate using the power rule. So I'm ready to actually take the antiderivative now. So this will be 1/8 u to the 8th. This one, I'll ignore the -2. That's going to become 1/10 u to the 10th, but I have a -2 out front. So -2 times 1/10 u to the 10th. And then this one's just plus 1/12 u to the 12th plus some constant. And this right here, when we put these together here, this will be a minus 1/5 because we're multiplying. So now I'll just replace all my u's with sine. So I should get 1/8 sine theta to the 8th power. And then here we said this is going to become minus 1/5 sine to the, 10th power theta. And then plus 1/12 sine to the 12th theta plus a constant of integration. Okay, that was 3. Let me take a look at 4. I can already tell that marker's not going to be good. Try a blue one. Integral sine to the 5th. Oh, wow, no. Okay, I don't know why people don't throw these things away. Oops. Sine to the 5th x dx. All right, so I have sine to an odd power, so I will factor one factor of sine out, right? But we have a problem here because we're supposed to let u be equal to cosine x, and I don't have, because what? The derivative of this is negative sine x dx, which I almost had there. I'm off by sine, so negative du will be sine x dx. But I don't have a cosine here. But that's okay because I can rewrite that sine in terms of cosine. I'm going to use the Pythagorean identity to do it. This is getting annoying. Hang tight, I'll be right back. All right, so what I'm going to do here, I'm going to throw all these markers away because none of them are good. So you're going to rewrite the sine to the 4th there. Maybe you've done this on your own already. You've been waiting for me. Rewrite it as sine squared squared. And then the sine squared you'll turn into 1 minus cosine squared. All right. So this sine to the fourth is sine squared x squared. Then I have sine x dx. So these markers are good, but they don't last very long. All right, and now this is integral 1 minus cosine squared x squared times sine x dx. So sine to the fourth is sine squared squared. Sine squared is 1 minus cosine squared, and then squared. So now I should be in business. I make my substitution that u is cosine x. So the integral becomes, in terms of u, integral here, 1 minus u squared squared, and then this right here, remember we have the negative, don't forget that negative, negative du. And now I will expand this out, multiply it out. So I have equals negative integral. We get 1 minus 2u squared plus u to the fourth du. And that negative on the outside, I could leave it there. I like to bring it in if I've got a polynomial like that. I just go in there and change all the signs of everything. So this is equal to negative 1 plus 2u squared minus u to the fourth du. And now I'll do my integration. Remember, u was sine x, I just erased it. And so we get antiderivative of negative 1 is negative u. Antiderivative here, we get a 1/3 u cubed, but there was a 2 out there, so 2/3 u cubed. And here I get minus 1/5 u to the fifth plus a constant. And u in this problem was sine. So I will say this is negative sine x plus 2/3 sine x to the third, and then minus 1/5 sine x to the fifth plus a constant. And that is it. These write good, but they don't erase very good. Put a little elbow grease into this to get this off. My goodness. Okay, number 5. Number 5, cosine squared. This was a test problem. Yeah, it was. All right, so on this one, we don't have an odd power. Okay, so when we don't have an odd power for sine or cosine, we have to use a different technique. And the different technique is to use the power reducing formula. So that means I'm going to use this formula. Cosine squared theta equals 1/2 times 1 plus cosine 2 theta. And we talked about that in class. So this formula allows you to take a squared on a cosine and get rid of the squared. So you notice this is not squared. But in the formula, you're going to get a 2 theta inside the argument. And then there's a bunch of other crap out here too. But it allows you to reduce the power, and that helps us because when we integrate, we can integrate that, relatively easily, I should say. All right, with relative ease. That's what I really should have said. Okay, so replacing this expression with this, the 1/2 is going to come out of the integral. I will have in here 1 plus cosine 2 theta, and that's it, d theta. And this integral, super clean. I can do the antiderivative of each one because I have addition, so it's 1/2, here's my antiderivative, and then let me go ahead and figure out what these are. Antiderivative of 1 with respect to theta is just theta. The antiderivative of cosine we know is sine, but because that's a linear expression inside, I have to scale by 1/a. And then this plus c, and distribute the 1/2 through, and you get 1/2 theta plus 1/4 sine 2 theta plus c. We're done. Number 6, sine squared of 1/3 theta. Sine squared, how do they write that? 1/3 in front? Yeah, 1/3 theta d theta. This problem is going to work exactly like the last one, except, well, because it's squared, we have an even power, not an odd, except that we have to use a different formula. We have a different formula for reducing the power on sine. It's this, sine squared theta equals 1/2, that's the same, 1, that's the same, minus, that's different, cosine 2 theta. So everything else in the formula is exactly the same as the last one, except it's minus. And it is a cosine here, it's not sine. So this is the formula. Notice I have 1/3 theta though. Okay, so that's going to be a little bit different over there. So this becomes integral, I have a 1/2 that comes out, 1 minus, and then cosine of 2 times whatever angle was here. So just 2 times that, which is 2/3 theta, d theta. So I just double the angle, right? 2 times 1/3, that's 2/3. And now, again, I can integrate this with relative ease. 1/2 here. Antiderivative of 1 is theta. The antiderivative of cosine is sine, and I have a minus here. And also, I have to scale, because this is linear in here, I have to scale by 1/a. So I do 1/2/3, which comes out to be 3/2. And then plus c. And then I can distribute my 1/2 through. And when I do that, I get 1/2 theta, distribute here to here, minus 3/4 sine 2/3 theta plus a constant. That's it. We're done. All right, number 7, cosine to the 4th of 2t dt. Ugh. I already know this is going to be ugly. Cosine to the 4th of 2t dt. All right, now the reason it's going to be ugly is because it's cosine to the 4th, so I can't do what I did when it was odd and just pull out a cosine. Because it's even, I know I'm going to have to use that power-reducing formula. The power-reducing formula for cosine I had up on the board just a second ago is this one. I'm just going to put 2 theta without parentheses. So since I have a 4th power, I'm actually going to wind up getting that thing, this thing, squared, which is going to give me another cosine squared at some point, which means I'm going to have to do the power-reducing formula again. So I already know, because this is to the 4th power, I'm going to wind up using that formula twice. So let me show you. So first of all, I'm going to rewrite this as cosine squared 2t, but then that's being squared. I could use parentheses, but I use brackets just for fun. Okay, so this thing squared, and then squared is to the 4th power. Now, we already know inside that bracket that we get a 1/2, 1 minus, plus cosine of 2t. Okay, that's what this is with the formula. Oh, sorry, hold on. Forgot to double the angle. I have to double whatever angle was in here, so that's not 2t, that's actually 4t. I'm glad I caught that. And then that's what's in my brackets, and that's being squared, and then dt. Okay, so this becomes this, but it's still squared. And now what I need to do, I cannot integrate. I can't pull the 1/2 out even because it's being squared. So I can't integrate each of these one by one because of the squared also. So let's try and take care of that squared. First of all, because this is multiplication, I can square this and square this. So that means it becomes integral 1/2 squared is 1/2 times 1/2, that's 1/4, times this thing squared is 1 plus cosine 4t. All of that squared. Notice the squared is no longer on this. We already took care of that. And then dt. Now, the 1/4 now can come out. So I have 1/4 that comes out of this problem. So 1/4 integral. Now what's still here? 1 plus cosine 4t, that quantity squared. Now I have to actually square this, which means I have to multiply it times itself. So let me take a little break here and do that. That means I have to do 1 plus cosine 4t times 1 plus cosine 4t. And then I FOIL 1 times 1. 1 times cosine 4t is cosine 4t. 1 times cosine 4t again is cosine 4t. And then the last one, which is very important, cosine 4t times cosine 4t is cosine squared 4t. It is not cosine squared 16t squared or anything like that. You're multiplying something times itself, which means it's that quantity squared. I can combine the middle two terms together to get 1 plus 2 cosine 4t, then plus the cosine squared 4t. All right, so this integrand becomes this integrand, and now I've split it up. I have 1, 2, 3 terms. So what am I going to be able to do with that? Let's see. Goodness. Okay. Integral. 1/4 was out here. All right, now all this. 1 plus 2 cosine 4t plus cosine squared 4t dt. So now we look at each one. Can we handle each one? Antiderivative of 1 with respect to t is just t. The antiderivative of this I should be able to do because it's just a cosine function. I've got an a in here, so I'm going to have to scale when I do this. But this one is a cosine squared, and I can't integrate that. And that's the one I'm going to have to do the formula on again. So let me take care of these two first. I'm actually going to find the antiderivative here. The antiderivative of 1 we said was t, but then times 1/4, because that 1/4 goes to all of these, right? So I have 1/4 t, no more integral sign there, right? Then the antiderivative of this one, let me just jot it down. I have a 2. The antiderivative of cosine is sine of 4t here, but then I have to scale by 1 over a, right? So that's going to become, these two together is 1/2 sine 4t, but then I have the 1/4 that distributes through and hits this and becomes a 1/8. So this next term is going to be 1/8 sine of 4t. So I've taken the antiderivative of the first two terms and I distribute a 1/4 through. This one I cannot find the antiderivative of right away. So I'm going to keep the integral sign on this one, remembering I had a 1/4 out here. So plus, right, plus 1/4 cosine squared 4t dt. I wonder if this works any better. Oh no, that does not. All right. Okay, at this point, I'm going to need to bring that formula back in. Okay, the formula, it's going to allow me to reduce the power on this one right here. So, using the formula, this integral becomes a 1/2, then in parentheses 1 plus cosine, and then double the angle. doubling that angle, I now have 8t dt. And the good thing here is I can pull the 1/2 out. It'll join up with this 1/4. And then I can integrate those term by term. So let's do that on the next line. I'll pull the 1/2 out, so I'll rewrite everything. Actually, I'm going to save myself some time. I pull the 1/2 out. This becomes a 1/8. And then this integrand right here is what's in parentheses here. So 1 plus cosine 8t dt. All right, now I have the pleasure of integrating each of these and just remembering that I have a 1/8 out here. So I'm getting to an answer here eventually. Just rewrite all this first. Plus 1/8. Now here's my antiderivative. Antiderivative of 1 with respect to t is just t. And then antiderivative of cosine of 8t is sine of 8t. But I have to scale it out in the front, 1/8. And then I've done the antiderivative, so plus c. And now what I'll do is I'll distribute that 1/8 through. You can see why I went, ugh, when I saw this problem. I kind of knew where we were headed. 1/8 t here to here, and then here to here is 1/64 sine 8t plus c. There is one more thing we can do. We can take 1/4 t and combine it with 1/8 t. You can't put the signs together because they have different arguments, 8t and 4t, so you can't put those together. But 1/4 t plus 1/8 t is what? 3/8 t? So let me just get rid of this one. And I'll change that to a 3/8 out here. 3/8 t. So it's this plus that plus c. All right. I've got to go in like half an hour. Got a meeting. Let's see what else I can do here. Look at number 8. This homework assignment is going to take forever to get through. If I do all the odds and evens, this is going to take a long time. Okay, number 8. Integral 2 minus sine theta, that whole quantity squared d theta. All right, so you look at this and you're like, okay, I could take the antiderivative of these individually, but it's being squared, so I can't do that. So why don't we just square it out? And I'm going to try and save us some time. I'm going to square this out in my head, and hopefully I'll get it right. 4 minus 4 sine theta plus sine squared theta d theta. So if you take this times itself, set them up, do the FOIL, collect like terms, you should get that. And now you look at each of these. Yes, I can find the antiderivative of 4 with respect to theta. Yes, I know the antiderivative of sine. Sine squared, on the other hand, I don't, because it's squared, so I have to use that power reducing formula. So let me knock out those first two integrals first. That's 4 theta. And then over here, be careful, forget the -4. Antiderivative of sine theta is negative cosine theta, but then you have a -4 out here already, so it becomes positive 4 cosine theta. And then plus this right here, which is an integral, because I haven't taken the antiderivative. And then sine squared theta, I'm going to use that formula, the power reducing, and I have to double the angle. So just 2 theta here, d theta. And the 1/2 can come out. I'm going to go a little faster on this one because time. So I pull the 1/2 out. The antiderivative of 1 with respect to theta is just theta, but then there was a 1/2 in front. So 1/2 theta theta would be my next term. And then, let's try this. What's the antiderivative of cosine 2 theta? Well, that's going to be 1/2 sine 2 theta, because the antiderivative of cosine is sine, then I have to scale by the 1 over a. But in front of that, I had a negative sign, and I have a 1/2. So I'm going to put a negative and then a 1/2 in times, because it's multiplication there. And now that's going to become, when you put those two together, you get negative 1/4. So minus 1/4. Just got to be careful with that, the signs and stuff. And then plus c. We're done. Unless we can put some stuff together. We can put the thetas together. 4 theta and 1/2 of theta is what? I can't think right now. 9/2 theta, 9/2 theta. So 9/2 theta plus this minus that plus c. So everything there. This plus this minus that. That's your answer. Okay, that's number 8. Let's go with number 9. Number 9, sine squared cosine squared. Sine squared x cosine squared x dx. All right, so for this, they're both squared. Since they're both squared, I can't pull out anything like we did when one of them was odd. But this power reducing formula has been pretty effective. So what I'm going to do is I'm going to rewrite the integral. Rewrite the sine squared x first. That's 1/2 times 1 minus cosine 2x, because I doubled the angle. Then I rewrite this, and remember there's multiplication between them, so times 1/2, then 1 plus cosine 2x dx. Now, because this is all multiplication, the 1/2 times the 1/2 is a 1/4. I can bring that out. So I've taken care of those two. They're outside now. And then these two, I'm actually going to FOIL these out. 1 times 1 gives me 1. 1 times cosine 2x gives me cosine 2x. But then negative cosine 2x times 1 gives me negative cosine 2x. And those two cancel each other out. Nice. Then you have this times itself, a positive and a negative, so it's going to be minus that cosine of 2x, but because it was times itself, it's squared, dx. All right, can you find the antiderivative of 1? Yes, with respect to x, the antiderivative would be x. Can we find the antiderivative of this? Yes, but we'll have to use the power reducing formula again. So let me try this. Antiderivative 1 is x, but I had a 1/4, so 1/4 x. And then, because I'm splitting this into two integrals, this 1/4 is going to come with us, and I'm going to put a minus here. So minus 1/4 integral, because I haven't taken the antiderivative, of cosine squared 2x dx. All right. So this one I took the antiderivative of, this one I have not. But the 1/4 had to come with me. All right, so now power reducing formula on that piece right there. So this becomes 1/4 x minus 1/4 integral, power reduce on that, 1/2, 1 plus cosine, double the angle, 4x dx. And we should be able to find the antiderivative of each of those individually. I'll have a 1/2 that comes out. So 1/4 minus 1/8, and then those two are taken care of. Let's find the antiderivative here. Antiderivative of 1 with respect to x is x. Antiderivative of cosine of 4x is going to be plus, because it's plus here. 1 over 4, because I have to scale by a, sine 4x. Parentheses. I use parentheses this time. Plus c. And then distribute the negative 1/8 through. So 1/4 x minus 1/8 x, and then distribute here to here, negative 1 over 32 sine 4x plus c. Put these two together, that's just 1/8 x minus 1/32 sine 4x plus c. What number was that? Was that 9? Yeah, that was 9. Oh no. Number 10, cosine to the 6th. That's a torture problem. I'm not willing to do that. Cosine to the 6th is just like cosine to the 4th, but you've got to apply the power reducing formula 3 times. I would never ask you to do that on a test. That's just, like I said, that's just tedious. I encourage you to do it because it really helps you with keeping track of signs. And I've done it many times. I've done cosine to the 6th, I've done sine to the 6th, I've done cosine to the 8th, and I've done sine to the 8th. In those you have to take it and do it like 4 times. It's even worse. And it actually turns out the times that I've done it in the past, here's my sheet of paper. I actually had to turn my paper landscape sideways to get it all to fit in because it was just such a disaster. But I'm not willing to do it here. To me, that would just be a waste of time. So there's nothing new in that problem. 3 applications of the formula. Lots of numbers to keep track of, constants to keep track of. But you'll be okay without seeing it, I hope. Number 11. T sine squared t dt. Integral t sine squared t dt. Okay, so this doesn't look like anything that we've done up to this point because you have a sine squared there, but you also have a t there. That t is not a trig function. And so what we've done in the past doesn't appear that it would work because of the t. So we need to kind of rethink this. Maybe there's something else we can do. So I'm looking at that and I'm thinking, okay, well wait, with integration by parts, if I pick like this to be u, the derivative of that is just going to be 1. And that's good because in my new integral the t will be gone. The problem with that though is that this would have to be dv and I have to be able to integrate it. So let me kind of explain what I'm thinking here. I'm thinking I'm going to let u be t because du is dt, and that's nice. Here, though, I would have to let everything else be dv, which would be the sine squared t dt. And now I've got to figure out what v is, so I've got to go up here on my table, which means I have to integrate that. And that's not an easy integral just that we know mentally. So what I'm going to do is on the side, I'm going to ask myself, can I even integrate that? Can I integrate sine squared t dt? Of course we can. We just did this problem. We use the power reducing formula. We get a 1/2 that comes out. We get 1 minus cosine, in this case 2t dt. So using the power reducing formula, remember the 1/2, I just pulled it out now. I can find the antiderivative of each of these, no problem, and then distribute a 1/2 through. So 1/2, antiderivative 1 with respect to t is t. Antiderivative of this will be, let's see, antiderivative of that is just 1/2 sine 2t. But then I come in here and make it negative 1/2 sine 2t, and then I hit it with a 1/2. So it becomes minus 1/4 sine 2t. That's the antiderivative plus a constant. But I'm not going to do that until I put this all together. I'll throw the constant at the very end. So that's the antiderivative of the sine squared. So look what we've done here. Integration by parts used to work for us because this became easier and this was something we could do pretty easily. Now you can see that this step going up might actually require some work. So that's okay, that's what we have. So this equals this answer, 1/2 t minus 1/4 sine 2t. And now when I look at setting up my ultraviolet minus voodoo, right? Voodoo, my diagonal here, is just going to be that new integral is going to be this times dt. But wait a minute, That just means I have to integrate this again, but that's an easy one to integrate. Antiderivative of this is straightforward, antiderivative of this is straightforward. So I'm in business. This answer will be ultraviolet, this times this. So how are we going to do that? Because this is two terms. Well, I just distribute the t to each one. So it'll be t squared, 1/2 t squared, because it had a 1/2 on it. So 1/2 t squared minus 1/4, then I'll bring that t in right here, t sine 2t, now minus integral of voodoo, which is this across. So 1/2 t minus 1/4 sine 2t dt. I guess I'm going to need all this space. Okay, I've got about 20 minutes the most, maybe about 15. About 15. Okay, so let's go ahead and integrate that now. So we have 1/2 t squared minus 1/4 t sine 2t, and then antiderivative of this. So cover up the 1/2. That antiderivative of t is 1/2 t squared, but then you hit it with a 1/2, it becomes 1/4 t squared, and then minus. So minus 1/4 t squared. And then, this is going to get a little complicated, but antiderivative of sine of 2t is negative 1/2 cosine 2t. You hit that with a negative 1/4, that becomes positive 1/8, and then you hit it with a negative again. So minus 1/8 cosine 2t plus now my constant of integration. And we can put the 1/2 t squared minus 1/4 t squared, that just becomes a positive 1/4 t squared. And then all of that. All right, what number was that? 11? I'm actually going to look at this one in the book. See if it looks the same. 1/4 t squared minus 1/4 t sine 2t minus 1/8 cosine 2t. All right, looks good. All right, what's next? 12. I think I'll skip 12. 12 is exactly like 11, except they use cosine squared instead of sine squared. So I'll skip 12. 13 looks interesting. I may have done 13 in class now I think about it. But this will be the last one I do on this video because I've got to pack up and get to my meeting. And this video is coming right on an hour here in just a minute, in just about 10 minutes, so that'd be good. So number 13. Cosine squared x, tangent cubed x. All right, so again, this does not fall into the category that we had earlier because we needed sines and cosines together if we were going to use any of those methods. Here we have cosine and tangent. But let's just remember that tangent is sine and cosine combined. So this is cosine squared x times tangent of x is sine x over cosine x. So this is sine cubed x over cosine cubed x dx. That's what tangent cubed means. And that's actually going to cancel out here. Those two cosines cancel with two of the factors of cosine, so I still have one factor of cosine there. So I have integral, let me write it this way, sine cubed x over cosine x dx. And now you look at that and you're like, well, what do I do with that? Because what you can't do is what we've done in the past, because the cosine is in the bottom, So you can't be looking at that as, oh, I've got cosine to an odd power. It's actually cosine to the negative one because it comes up like that. But let's just see. Maybe there's still a way we can do it. I know that the derivative of cosine is sine. I know the derivative of sine is cosine. I don't want to choose sine to be my u because the derivative of that's down here. So I'm thinking basic substitution here. If I choose u to be cosine, the derivative of it's up here, but then it's cubed, and I told you to avoid that. You want to avoid your derivative being trapped somewhere. But maybe there's still a way I can do it. So this is where things start to get real weird, because it's like now you're going to do something I told you to avoid. But you just got to kind of take swings at this thing and hope that things work out. If not, your other option is to not even try, which isn't an option, right? So I'm going to peel off one sine because I know the derivative of cosine is negative sine. So that'll give me my du. I just need to resolve the sine squared. But sine squared is 1 minus cosine squared. So that top is 1 minus cosine squared x over cosine x, and then sine x dx. And now I've got everything over here in terms of cosine, which is going to be my u, and the derivative of it is out here, basically. I'm off by sine, but I'm going to let u be cosine x. Du is negative sine x dx. Negative du is sine x dx. So let's rewrite this integral. Integral 1 minus u squared over cosine of x was u. Then sine x dx is negative du. So here's du. Here's your minus. Very good. Now, because I have a single term in the denominator and 2 on top, I'm going to just split this into 2 fractions. It'll be 1 over u, and then the other one minus u squared over u, which is just u, and then du. And I'm going to do what I did earlier. I don't like the negative out here if I've got 2 terms, so I'm going to distribute it. It's going to make this negative and that positive. So I'll switch the order. I'll put the u first as positive, and then minus 1 over u, du. And now just antiderivative of that. So antiderivative of u by itself is 1/2 u squared. And then the antiderivative of 1 over u is natural log of the absolute value of u plus a constant. And now all I have to do is go and replace u. And this answer is really strange because if you remember what we started with, look at what our answer is. U is cosine x, and I'm squaring it, and then minus natural log of cosine x plus c. So our original integrand was what, like sine cubed? No, sine cubed? What was it? Oh, cosine squared tangent cubed. It was cosine squared tangent cubed. And our answer has natural log in it. It's kind of strange. All right, but that's it. So I believe that is going to be all I can do right now, time-wise. And that'll be it. Yeah, I'm getting a text. It's probably that I need to get to this meeting. All right, I'll see y'all again soon.